All right, problem 7 of exam 4. We got a man standing on a platform. It's rotating without friction. He has an angular velocity of 1.2 revolutions per second. His arms are outstretched, and he's holding a brick in each hand. If you'll remind me, we'll do this in class next time we're together. So, the rotational inertia of the system consisting of the man, bricks, and the platform about the center axis of the platform is 6 kilograms meter squared. If by moving the bricks, the man decreases the rotational inertia of the system to 2 kilogram meter squared, what are A, the resulting angular speed of the platform, and B, the ratio of the kinetic energy of the system to the original kinetic energy? All right, so let's get started. This is a conservation of angular momentum problem. And so we know that the L initial is going to equal to the L final. Angular momentum is going to be equal. Now, this is just a platform rotating. We don't really have to worry about the direction. Direction is constant throughout all of this. So the initial angular momentum I omega equals the final angular momentum I final omega final. Let me put an initial subscript on the initial angular momentum, initial moment of inertia. So we know angular momentum is conserved, right? So I initial omega I equals I final omega F, right? All right. And what we're after is what is omega F. So I initial over I final onto omega initial. And so we have 6 over 2 onto 1.2 revs per second. And that's going to give us 3.6 revs per second. Right? That's the final angular velocity, right? Angular speed, 3.6 revs per second. So it goes from 1.2 revs per second to 3.6 revs per second, increases by a factor of 3. Okay, so now we want the ratio of kinetic energy of the system to the original kinetic energy, right? So kinetic energy in a rotational system, 1/2 I omega squared, right? We want the ratios of the two, so we want K final over K initial, which is going to be the 1/2 will cancel, I final omega final squared divided by I initial omega initial squared, right? Okay. So let's see. Oh, there's some things we can do here real quick, or we could stick the numbers in, but I'm going to parse this out a little bit. So we got I final omega final divided by I initial omega, not that omega, this omega initial equals, nope, times, and now the other term omega final divided by omega, omega initial. Okay, you might look at me like I'm crazy because I did this, but this is the ratio, this first term is the ratio of the final momentum, angular momentum, to the initial angular momentum, and that is simply 1. And so we end up with, right, that's 1 because they're equal. And so we end up with this, omega final to omega initial, which is 3, right? That ends up being the ratio, well, we could write it this way. Equals 3, right? And that gets it back to things that we did not have to calculate, which, as a computational guy, I always like to start with things that we did not have to calculate. All right. Anytime you can take everything back to something you didn't have to calculate, your number is a better number. All right. That's it. We get an answer of 3, and that's it for this test.